it allows us to explain phenomena that can't happen in classical physics, such as single particle interference and entanglement. Quantum mechanics has some importance in technology, as it is needed to design optical and electronic components, which often take advantage of certain quantum mechanical effects. It also is important for the theory of computation, which we'll talk about later. So according to quantum mechanics, it is possible to build a universal quantum computer that can simulate any physical system, our real world. This means we can test theories about physical systems by simulating them and then checking the results and compare it to what reality is like. Okay, so let's talk about the applications of quantum mechanics in our daily lives. So we have MRIs, which I'm sure some of you guys have heard of, our cell phones, lasers and telecommunication, that's our cellular networks and internet, and then atomic clocks and GPS. So first we're going to talk about MRIs. So MRIs stand for magnetic resonance imaging. And so the central basis of how MRI works is it uses NMR. Now, if some of you guys have taken, Chem 261, 263 organic chemistry labs, you might have heard of NMR. And it works by measuring the flipping in spins of the hydrogen atoms. And so the clever arrangement, so what the MRI does is it produces a magnetic field. And so there's a clever arrangement of the magnetic field lets doctors measure the concentration of hydrogen appearing at different parts of our body. And so the different parts of our body have different levels of hydrogen, right? And so this allows us to distinguish between hard and soft tissues, which is better than traditional x-rays. Okay, let's talk about lasers and telecommunication. So the key physics of lasers is really contained in Albert Einstein's paper in 1917, which, I mean, what a coincidence, Dr. Solis has Einstein in his background today. But so in his paper, he wrote on the statistics of photons. Although the term photon was coined later in his paper, their interactions with atoms. So he introduced the idea of stimulated emission, where an atom in a high energy state encountering a photon of just the right wavelength is induced to emit a second photon identical to the first one. So this process is responsible for light amplification, also known as the simulated emission of radiation. So that whole thing, like light amplification by stimulated emission of radiation, that's the acronym for laser. So that's how the word laser came to be. And so in quantum mechanics, it is also used in fiber optic telecommunication. So fibers themselves are pretty classical. There's nothing new there, but the light sources used to send signals down the fiber optic cables are lasers, which are quantum devices. So anytime you use a laser, whether indirectly making a phone call or scanning like a QR code in groceries, you're using quantum mechanics. So it's really practical in our daily lives. Okay, so atomic clocks. Now this one's interesting. So one of the most common uses in our internet connected smartphones is to be able to find directions, Google Maps, Apple Maps. So smartphone navigation is enabled via like GPS. And so GPS uses just a network of satellites above our atmosphere in space, orbiting the Earth. And how it measures our precise location is it receives signals from multiple satellites, and each satellite has its own atomic clock. And so it calculates the exact arrival time of the signal, right? So usually you need at least 3 satellites at once. And so the way it positions you perfectly, not perfectly, very close, is that the 3 satellites measure the difference it takes for the signal to reach each other. And so that difference is so precise, right? Because light travels at 300,000 kilometers per second. And so the only way you can measure that level of precise timing is using atomic clocks. And so the basis of atomic clocks is quantum mechanics. So the computer inside the receiver of the satellite does some math to figure out the single point on the surface of the Earth, that is the distance between the satellites. and it can locate you within a few meters. And so the mechanism relies on the fact that the speed of light is constant, right? And the only thing that's different is distance between you and the 3 different satellites. So you have this GPS constellation, and each GPS has its own atomic clock. And so these rely on the quantum mechanics, the ticking, basically. And so the atom inside each atomic clock is rubidium. And so it oscillates. Well, as it oscillates, it releases microwaves, which is, a form of light. And it oscillates because it transitions between 2 quantum states. So this quantum state, this transitioning quantum state, is a quantum mechanical effect. And so we're utilizing that quantum mechanic to achieve a very precise form of timing. Okay, now let's talk about computers. So, we use computers every day. And really what a computer is it's an information processor. So it takes raw information at one end, stores it until we're ready to use it, and then it can spit out a result at the other end. And so, we all talk using words, we have sentences. So how do computers talk to each other? They talk to each other using binary numbers. And so binary digits instead of how we use decimals. So the word bit is the shortened of the word binary digit. So it's like the B and I and the IT of digit. So whereas decimal digits have 10 possible values, from 0 to 9, bits can only be 0 or 1. That's no or yes. Therefore, a binary number is composed of only zeros and ones. So bits are really small, and we just never use bits anymore. We're way more advanced now. And so bits are usually assembled into a group of 8 to form a byte. So sometimes you might hear a gigabyte or megabyte or megabit. I learned this one recently. I was getting internet, and internet companies these days they flex their speeds, right? Like 100 megabits per second. I always thought it was 100 megabytes per second, and so every time I download, I definitely don't get 100 megabytes. I get like 4 or 10 megabytes per second. So I'm like, I'm paying for 100 megabytes, right? But it's actually 100 megabits, right? So it's 100 divided by 8, and then that's your true speed. So there's a difference between megabytes and megabits. Okay, next slide. So what are quantum computers now? So quantum computers aren't limited to just 2 states. So before, the 2 states for classical computing was 0 and 1. So no and yes. Rather, quantum computers encode information in quantum bits or qubits. And just the basics of quantum mechanics is that things can exist in a superposition. Just like previously, the atomic clock, we had rubidium that was transitioning between states. So we take advantage of this quantum mechanical effect of superposition. So rather than 0 and 1, a qubit is 0 and 1 at the same time. Okay, it's pretty wild. So the qubits, what are qubits, right? So qubits are atoms, ions, or photons or electrons, right? So that's what they are. Inside their controlled device, and they're working together to act as like the computer memory or the computer processor. Now, because quantum computers can contain these multiple states simultaneously, 0 and 1 at the same time, it basically means it has the potential to be like millions and millions of times more powerful than the most powerful supercomputer we have today. And the most powerful supercomputer we have today is a classical computer using zeros and ones. So quantum computers can solve problems that are basically impossible to solve with a traditional computer. Imagine like decrypting the strongest passwords or simulating weather, right? Weather has like so many different particles. You have like oxygen, nitrogen, carbon dioxide in the air swirling around. Like that's literally impossible for a classical computer to do, but very possible with a quantum computer. So today we produce around 2.5 exabytes of data. That number is like equivalent to the content of 5 million laptops. So that's crazy. Every day we're producing 5 million laptops worth of data. So quantum computers will make it possible to process that amount of data. In order to keep quantum computers safe, like you have a picture here of the quantum computer that looks nothing like our laptops and desktops we have at home. And so to keep this kind of computer cold, they need to be held at minus like 460 degrees Fahrenheit, right? Which is very, very cold. So rather than use electricity, quantum computers will reduce the power consumption up to like 1,000 times compared to classical computing. And that's because of the phenomenon called quantum tunneling. So I don't know if you guys have heard of that. Right now, there's like two major processor companies. There's Intel and AMD. And Intel used to be like a monopoly. And just recently, AMD started releasing some really good products. And these two companies, they're flexing their, how do they like get the customer interested, right? And so one metric they talk about is the processing, the manufacturing node, which is how small their processor is. So right now Intel's on 14 nanometer, and AMD recently was talking about their 7 nanometer, right? So smaller to the customer sounds like, you know, it's really advanced, which is true. But once you get too small, then electrons aren't trapped in their lanes, right? They can start tunneling through. So quantum tunneling is when electrons can start passing through solid barriers. And so that's the limit of classical computing. So AMD, Intel, they're using their classical computing chips, and they're going down and down, right? 14, 7, going down. There's going to be a limit for them because they can't keep their electrons in the same place because they're going to tunnel. And so that's where quantum computing comes in. All right, so there's a quick table of like the difference between classical and quantum computing. So classical computers are better at some tasks than quantum computers, such as our daily tasks like email, spreadsheets, or like, you know, gaming, stuff like that. You're not gonna really game on a quantum computer. It's just, it literally isn't meant for that. You know, looking back at this picture right here, like, have you guys seen what like the supercomputers look like these days? That Google has or IBM has? Like their computers take up an entire room. You know what I'm saying? Like an entire basement is just computer. Whereas this thing, you know, that's like the size of maybe a microwave or something. Although it's encapsulated and kept really cold, like that's more powerful than the modern day supercomputer that's like liquid cooled and the size of a room, right? So there's just so much potential here. And so really the intent of quantum computers is to be a different tool to solve different problems, like not to replace like a classical computer. Okay, I want to show you this video. I think this video does like a phenomenal job of like quickly explaining what quantum computers are, and it has like pretty cool animations as well. Also, let me know if you can hear the audio. I'm not sure if the computer is able to share the audio. Let's see. Okay.
Yes, so I think we're not getting the audio. I also haven't been able to share like this.
So you guys aren't hearing any audio right now?
No.
No. I think
Okay.
when you share, like if you unshare your screen first and then you share it again, when that box pops up, there's at the bottom left-hand corner, you can click a box that says to share your computer audio.
Okay. I'll make sure to do that. Okay, let me unshare and then share. Let's see. I'm trying to get to these meeting controls. Are they? Oh, they're over here. I see. Okay. So I'm gonna stop sharing and then reshare.
Yeah, and I think there'll be an audio.
Right.
There.
I see it now. Sorry about that. All right. Round 2. Okay. Tell me if you can hear it now.
Yay!
Quantum
Awesome.
physics, one of the most successful theories of modern science, describes the way our world works at the most fundamental level. Quantum computing has become one of the leading applications of quantum physics. Quantum computers have the potential to solve some of the world's most complex problems that are beyond the reach of even today's most powerful supercomputers. Quantum computers are not going to replace classical computers, but their radically different way of operating enables them to perform calculations that classical computing cannot. Let's see how they differ. Classical computers encode information in bits. and each bit can represent a 0 or a 1. These zeros and ones act as on-off switches that ultimately translate into compute functions. To perform a simple calculation, like solving a maze, a classical computer would test each possible route one at a time to find the correct one. Just as classical computers have bits, quantum computers have qubits. Qubits, however, make use of two key principles of quantum physics: superposition and entanglement. Superposition means that each qubit can represent a 0, a 1, or both at the same time. And entanglement happens when two qubits in a superposition are correlated with one another, meaning the state of one, whether it's a 0, a 1, or both, depends on the state of another. Using these two principles, qubits can act as a much more sophisticated version of switches, helping quantum computers solve difficult problems that are virtually impossible using classical computers. To illustrate how this makes quantum computers more powerful, let's look at some numbers. Take a classical n-bit computer, with n representing the number of bits. It can represent and examine only one system state at a time. An n-qubit computer, however, would have the power to represent 2 to the power of n system states and perform parallel operations on all those states at once. This means that every time you add just one more qubit to a quantum computer, the number of states it can represent and examine doubles. So a 50-qubit quantum machine could examine 2 to the power of 50 states at once. This exponential increase in power, together with the entanglement of qubits, is what allows quantum computers to solve certain problems so much more efficiently. While a classical computer solves a problem like the maze by testing each possible route one at a time, a quantum computer uses its entangled quantum states to find the correct route quicker, with far fewer calculations. Think of it this way. Technologies that currently run on classical computers can expertly find patterns and insights buried in vast amounts of existing data. But quantum computers will deliver solutions where patterns cannot be seen because sufficient data does not exist, or the possibilities for discovering an optimal answer are too enormous to ever be processed by a classical computer. Quantum computers could lead to the discovery of new medicines and materials by helping us untangle the complexities of molecular and chemical interactions. They could help the financial services industry make better investments by finding new ways to model financial data and isolate key global risk factors. They could even transform supply chain and logistics by finding the optimal routes across global systems, like optimizing fleet operations for deliveries during the holiday season. Quantum computing won't replace our everyday computers and smartphones, but its ability to solve complex problems will open up a new universe of information, transforming our view of the world and the way we navigate it.
All right. Pretty good video, in my opinion. Okay. So the next slide we're going to talk about in this lecture is called quantum supremacy. We haven't even touched on that yet. So what quantum supremacy is in quantum computing, quantum supremacy, the goal of demonstrating that a programmable quantum device can solve a problem that a classical computer practically cannot. Or it can be a demonstration that a quantum device can solve a problem faster than a classical computer. So basically what quantum supremacy means is the time when a quantum computer can do the job better. So let's look at like the amount of money that's being spent on quantum computers right now. So I mean, right now, this is I think the one time where the like other parts of the world are spending more than the United States. So the European Union, you know, they're spending a bit more than the United States here. So although the leaders right now in terms of private enterprises are like IBM, Google, and Intel, Microsoft that are building the most powerful quantum computers at the moment, which are all US-based companies. So Google's talking about achieving quantum supremacy, which means that they think they've built a computer that can do one task better than a classical computer can right now. So let me show you that video real quick.
The tantalizing promise of quantum computers is that they can do certain tasks exponentially faster than classical machines. And the quantum supremacy experiment is proof that this is indeed the case.
The word quantum computer is a little bit misleading because it sounds like a computer. And when people think of computer, they think of a phone or a laptop. The truth is the phone and the laptop and even a very powerful supercomputer all operate according to the same fundamental rules. And a quantum computer is fundamentally different.
The classical bit stores information as a 0 or 1, and a quantum bit can be both 0 and 1 at the same time. If you have 2 quantum bits, then there are 4 possible states that you can put in superposition. With 3 qubits, it's 8, 4 qubits, it's 16. It grows exponentially.
The nice thing about quantum supremacy is that it is a very well-defined engineering milestone.
In a nutshell, what we're trying to do is we're trying to show that experimental quantum computers can surpass the best supercomputers in the world.
To actually demonstrate quantum supremacy, we have these 3 steps. First, pick a circuit. Second, run it on the quantum computer. Third, simulate what the quantum computer is doing on a classical computer. We gradually increase the complexity of that circuit. And at some point, it becomes completely impossible for the classical computer to keep up. Then we say we've achieved quantum supremacy.
We started building together the quantum chips to do this experiment. And then the evolution of the devices with more and more qubits and more complexity. It's very much an iterative process.
A lot of the work that we put in was not just these chips, but is also the infrastructure that you need to drive those chips. The cryostats that we install them in, all of the control electronics, software, all of this stuff is needed, and it all has to be developed.
When the experiment started, we were getting data from the experimentalists. We saw initially a beautiful straight line corresponding to our predictions.
Then, right before we hit supremacy, it dropped much faster and it fell below the threshold where it needed to be.
And there's nothing we can do because we don't know how to analyze past that. So everyone's like, oh, we're screwed because it's getting really, really bad at large number of qubits.
It's like, well, maybe there's some really complex interaction between all the qubits.
It turned out that the reason was rather benign. We calibrated a little bit better and then this problem disappeared.
So there wasn't like oh, we did it.
I think we crossed it, and then it wasn't clear that we crossed it, so we crossed it a little bit further.
It took me like a day to realize, like, hold on, this is actually experimental data. It's kind of amazing to see, how well the theory works.
The processor that achieved quantum supremacy is called the Sycamore processor.
And it's parallel processing 2 to the 53 states, which is 10 million billion. And thus that enormous amount of parallel processing is what gives it the power.
When we run small chunks of the computation, it's the largest supercomputer in the world. Our estimate is that it will take thousands of years to complete the full computation.
Technologies are born this way. Let's say the space age started with a satellite orbiting Earth, and it was not doing much, it was just beeping.
The big technical achievement of quantum supremacy was really dependent on all this young talent who's kind of taken this and gotten it to work at a very technologically capable level.
We have reached a new computational capability. There are certain computations, the only place in the world where you can compute those things is here in our data center at Google Santa Barbara.
For the first time, we're showing that we can solve a problem that is just infeasible to do on the biggest computers ever made by civilization.
And what's exciting is now we're ready to turn this over to the world and say, let's figure out what we can do with this.
The thing that excites me most is building a useful quantum computer. When we can give a researcher a tool that is unlike any other and say, great, figure out something cool to do with it. Mankind is pretty good at that.
Gosh, that was so inspiring. Okay.
Yeah.
Very good. Okay, so I'm going to end with the
Who
last...
was it that said, if you think you understand quantum physics, you don't understand quantum physics?
Let's see here. Let's pause that. All right. So I want to end the very last point, which was talking about the ethics involved with quantum computing and mechanics. So one of the most widely used cryptography systems right now is the RSA public crypto system public key, which is used to encrypt our emails, our bank transactions, credit cards, using the internet. And so the security of these messages are encoded in this encryption method relies on the fact that factoring a large number is extremely difficult to accomplish using our everyday computers. So it's just the fact that it's just so hard to decrypt, okay? And with that being said, a quantum computer using an algorithm such as like the Peter Shor's factorization algorithm can factorize any number way, way faster than any of our normal computers can. And so that means that given as our quantum computing power increases with enough qubits, you can basically break any encryption key that exists today. And so is there virtually an unbreakable, is basically any encryption like safe, right? Quantum computers are going to change the landscape of our data security, even though quantum computers might be able to have like many different ways of cracking these encryption keys. Some people say that as quantum computers get better, so too will hack-proof replacements, right? So that's what people say. It's like win, 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 win. So I want to leave off with like, should we fear it or should we embrace it? This quantum computing. I often think of it kind of like genetic modification, very, very different landscape. But once quantum computing or genetic modification really picks up, it really completely changes our way of life, right? So if we think that quantum computing is inevitable, then we have to accept that it's going to be a major paradigm shift in our lives. It's going to be a completely new way that we live, right? When you think about the advancements in biology, right? Simulating protein folding it takes like multiple days to do. Whereas if scientists have the tools of quantum computing, they can just run that like a YouTube video, just simulate it instantly. And so that also means like more efficient understanding of all the complexities in the cell, whether it be like DNA transcription or genetic modification. And so you got to think about quantum computing as a completely new tool for humans, right? When the computers came out, it gave us new tools to do emails, to do spreadsheets, word processing. This is a completely new tool. And what's crazy about it is it basically makes our current infrastructure obsolete, right? We have all these things in place like security and stuff like that. And it just goes out the door because now this thing can solve it, crack all of them instantly. So it's going to be a huge change in how we live our lives, right? I mean, we already have issues with data security. People think our phones and stuff are getting hacked. Think our phones or webcams are getting hacked. Some people put like tape over their webcams, right? I mean, with quantum computing, that's like a guarantee at this point. So I want to end with like, how do you see our world changing when quantum supremacy is no longer just an infancy, which is it is right now, and it's just up and running and it's just perverse. So thank you very much for listening to my presentation. Do you guys have any questions? Any thoughts? When we share some like immediate thoughts, like do you think it's a good thing, not good thing? Excited about it, don't care.
That was super interesting. I have a question on your last slide.
Yes.
On a world without privacy and all of this. You're right. I think that if there is a computer that can simulate, for instance, in our field, Hadija and I work in lab research. So
right.
Imagine if all our experiments can be run in a computer and we get the results right away, then what does that mean for us as researchers of the future? And should we be beginning to embrace this rather than saying, no, I want to keep my job and machines came here to take my job? So should we begin then maybe doing this transition, because there will be a time period, I guess, in humanity where we will do the transition, but slowly. For instance, Hadija and I could do our experiments and at the same time use the quantum computers to see if what the computer predicts is actually what is happening in reality. Do you think that we need to work on this transition actively rather than wait until it happens?
I mean, 100%, you got to do it actively, right? I don't know if it would be so sudden. It's like tomorrow you wake up, suddenly just every lab has a quantum computer. It might not work like that, but it's a new tool, right? And you bring up a good point, like, does quantum computing take away jobs of researchers? If our goal for humanity is to be much more scientific, much more accurate, and just have much more abilities to humans, then quantum computing is definitely a positive in that sense, right? Researchers don't have to waste time doing experiments when the quantum computer can already simulate it, right? That's just wasting time. And you talk about jobs, right? That's a great question. Like, I don't know all the answers for sure, but some people say, like, as we get more and more scientifically developed, new jobs appear from that. Before, we worried about like horses, like what will horses do? We had cars. Now people use the horses for fun, right? They ride horses for fun. That's just a simple example. That's what some people say. I'm not sure. It's all speculation, right? Like, as one thing advances, do different jobs, different positions appear, right? Someone's gonna have to code those quantum computers, right? And so that's another job now. Repair the quantum computers. I'm not sure, but that's a good point. Or maybe it reaches a point where, like, when there's all AI, and as Dr. Solis always talks about, right, the technological singularity, when no matter what, AI just does everything better than humans. And so then the purpose of our living definitely changes, right? It's not really improving humanity when AI can do it better than we can. And so then that's another discussion, right, down the road. Like, then what's the point of living? Stuff like that.
So what I think the students in this course should realize is David Pearce doesn't think computers will ever be able to think the way we are. The sort of continuous, the continuity of you feeling you've been you your whole life kind of thing. You don't have much question about that your experience today is directly, connected to previous things in your life. That feeling he feels, and this is related to what he calls the binding problem, he feels that that there's absolutely no proof that computers will ever be able to be really conscious the way we are, in a kind of continuous way where you feel this sense of self and so on. So I don't know if that's right. I mean, a lot. You'll see a lot of discussions on Facebook and LinkedIn and so on, where he is basically saying, well, that just can't happen. I don't know, but you have in this course talked directly to somebody who really feels like that computers can do amazing things that are different from what human beings are doing. But what we do in conscious processes, he thinks, is not possible for computers to do. And it's related to other things about, is consciousness just the activity of the brain, like, a mechanical property, or is it something more? So do any of you have intuitive feelings about David Pearce being right or wrong? And it's not unrelated to quantum, because people bring up to him the fact that quantum computers are going to be so powerful that, how is it possible that these computers won't be, in some sense, conscious? They obviously will, maybe. So I just wanted you to be aware that debate is quite active, and you have talked directly with one of the people involved, and a lot of people in a simple sense use quantum to show that there are no absolute barriers, that as Simon says, it's like a lot of amazing things that you couldn't do with ordinary computers, you will eventually be able to easily do with quantum computers. So life is sort of limitless in that sense. There are not absolute bounds to what we can achieve as humans, thinking about it that way.
I thought this was a very, very fascinating presentation, Simon. I quite enjoyed it. And the last slide, you sort of touched on the ethics part, and I'm really curious what your thoughts are, or anyone's thoughts, essentially on, if there is, we're approaching quantum supremacy, and the more it starts to take over, everyday functions of lives and research and scientific discovery, the more it'll actually start making decisions potentially on behalf of humans. So my question is, how do we decide what framework of ethics is used, or morals, in order for those decisions to be made? Because, even in the field of ethics or health ethics right now, healthcare ethics it's very individualized based on the patient. Some patients, they have a diverse background or a religious background that it differs from others, and that influences the ethics and the morals. So, how do we reach a sort of consensus as to what the moral framework would be in decision making with quantum supremacy?
One very positive thing that has happened in this course, Michael Van Manen has agreed to give 2 teaching sessions about ethics of the future. And you remember that the previous time that he spoke on September 22nd, was talking about how the stuff we're talking about is so beyond what he feels able to talk about. But anyway, so I think that this will be an interesting meeting of the minds of somebody who deals every day with important ethical questions of these very tiny children born prematurely and stuff, and all the considerations about them. But he's willing to kind of expand that thinking to all these other questions, because otherwise he wouldn't agree to give 2 full-length teaching sessions where you guys can ask him about all these other things. So that's good. And I think, so we'll be able to get the thoughts of a number of very good people. Also, Insu, the other guy who spoke during that session.
But Simon, so what are your thoughts on the ethics of the future? Could it be individualized to each patient, or will it be a consensus for all the patients?
I think that's a great question. I'm definitely by far the opposite of a clinical ethicist, but I think this is a really good point between if the AI does it better versus valuing our autonomy, right? Let's say making a decision on one patient. As humans, we have that feeling that our decisions, right, our autonomy is superior, right? But if the research and the facts is that the AI does a better job, right? And as Joel said, they start making decisions on our behalf because we trust them, because it's so far the evidence is that they make decisions better than us. Then how do we reconcile that with our autonomy? And you said on a patient individual by individual basis. Can you go more into that, like individualized healthcare, or?
Well, I mean, I think the example. So I took a healthcare ethics course,
Right.
and a lot of the individual patient care, the advice a health ethicist would give a patient and their family really depends on their their cultural background. For
Right.
example, certain religions may want a different end of life procedure than another religion, right? So
Right.
it's sort of those nuances, the human cultural touch, I guess, that how do we fine tune AI to take those into account as well?
Right. Yeah, I guess AI would factually, like, let's say we put in inputs like, is the patient feeling pain, or like what's the prognosis of the disease, and AI could probably figure out the best response a doctor could give, right? Like, should this patient continue suffering, or should they consider other options, right? Another input could be, like you said, culture, right? And if the culture is completely against like palliative care or the opposite, then that could be like a yes or no for the computer, right? Like a dichotomous key, kind of.
Yeah, gotcha.
And that's my opinion. That's not the truth. That's just my opinion. And I just thought of it just now, right?
So
But
there will be phases, I think, like there will be the initial clunky phase where people are dissatisfied and sort of out of syncness between what the sentient computers are doing and what we're doing. Then there'll be a sort of collaborative phase, which could be very satisfying, where because we understand nature and human beings better than computers do for the moment, they need us and we need them, and we're working together. But eventually they'll be able to learn everything we know about nature and humans and so on. And so maybe at some point they won't need us. They'll be completely independent. And so anyway, but if it's a world in which they still enjoy working on our behalf, that could still be a really good world, even if we reach a point where we can't understand what they're doing, but we understand they're still motivated to be helping us, and that is possible, that outcome would occur. And they could enable things like this multiple instances of self that would just be impossible now. You can think the only people really running simultaneous lives are criminals and actors, right? So pretending to be someone else, right? But in the world of the future, that'll be quite common to want to do that and to be able to successfully do it as multiple instances of self, not where you're doing something illegal or dishonest. And this collaboration with quantum computers could allow that to work really smoothly, where you never got the two lives mixed up, and it's very satisfying because your internal psychology wants to achieve certain things that it would be hard for just a single person to do. But if you have these multiple manifestations of yourself, you can easily do that. So it is partly like, if you think of the self-fulfilling prophecy, right? If we in this course make positive self-fulfilling prophecies where we think it could work like this, then maybe that could really happen, It isn't just that we're victims of the future and just trying to predict what will happen. We can also kind of shape it to a certain extent by talking about scenarios. And
I think that sense of, that idea of a little bit of denial at first, and in which we will be against machines making decisions for us, but also the idea of collaboration, those will happen simultaneously.
Yeah.
I don't think they will be happen one after the other, but they will be happening at the same time.
Sure.
There will be people that think, okay, let's use this to move forward, and at the same time, people that resist it. Maybe because it's, they could see it as, oh, it's against nature, or I don't know what not. But maybe this is part of the evolution of humankind altogether. So I am interested in the third question that says, what if the power of quantum computer falls into the wrong hands? And Simon, do you know if there are mechanisms or someone has already begun figuring out what to do in case it falls into the wrong hands, into, let's say, a megalomaniac that wants to rule over the world? How to stop that? Is there a plan already in place, or are there labs working in that?
Right. Definitely, I haven't read into that at all. I know, like, right now the limiting factor of it falling into the wrong hands is just like resources and money, right? These are like massive companies, many of it with government grants, that are able to like even attempt to build these things. So definitely no like independent evil organization can build these yet. But if you think about just like nuclear bomb, it used to be a big deal. Einstein said it wasn't possible. But now, I mean, there's just blueprints of the nuclear bombs. Like, apparently someone in a garage can make one, right? So I'm sure there's gonna be one day when the technology's out there and any person can make one, right? And so I think we just have to, like, how are like nuclear bombs not made in garages every day? I'm sure some are made, right? But that's a great question, like, to have that framework ready, because this is like crazy power, and eventually it'll be in the smartphone, right? Eventually, somehow, like, it'll just keep going down, and then it'll just be ubiquitous. Everyone, like, whenever they need to hack someone else, they just pull out their smartphone and do it, right? So it's definitely going to be a completely different reality in which we live in.
Yeah, I have a comment on that. So Simon, I don't know if you've seen The Social Dilemma or anyone else has on Netflix. I watched it yesterday, and it's kind of about really the basis of technology and how they're using principles in psychology to alter our reward center, like Instagram, Facebook, Snapchat, all those different technologies. And it kind of comes back to, do we need to prepare? The second question, do we need to prepare for a world without privacy? So are we already without privacy, do you think, Simon?
Oh yeah, for sure. I was talking about, like, people putting tape over their webcams, or, the election getting hacked or something like that. We definitely have way less privacy than we think, right? I'm sure, like, our phones are probably listening to us, like the microphones, right? Like, Google says they don't, but, like, why not, right? And it's all part of the big data. You need to collect massive amounts of data to improve the AI, right?
So do you think we should slow down with that? Like, do you think that it's getting out of hand and that our privacy shouldn't be something that can just be mined?
Right. I know our privacy, compared to like the 1950s, where all you knew was just your townspeople, compared to now, we have way less privacy, right? So perhaps we just have to accept that as we become more connected, the definition is that we become less private, right? And I guess there's some privacy in the numbers that we have, right? Like, you feel really secure because, like, the Google's listening right now, right, to this presentation, possibly, I'm not sure, but I'm not worried because they're listening to like billions of other people, right? So I feel that privacy in the sense of numbers, not that that's ethical that they're listening, but there's that sense that you have more anonymity with more people. But you're right, like, I'm not sure if our privacy can be maintained at the level it is now, or just inevitably just more and more connected. And then, Dr. Sola has this world of like multiple instances. At that point, you're sharing 7 versions of your privacy with like every other person on the same network, you know what I'm saying? So maybe it's just a different way we're going to be raised, where like privacy is just less, right?
So what will become apparent, I think, is that the idea of you being boring, which is never desirable now, but that will protect you, because if we're all being surveilled, the more boring and mundane and uninteresting you look, the less is the chance that somebody's really going to listen or watch, right? So, and so there probably will be ways to try to simulate what everybody accepts is boring and uninteresting, to make what you're doing look like that when you're actually doing something that lots of people would want to copy, know about, and so on. It's a whole other strategy of life of trying to, but part of it is also looking like you're conforming when you're not. Like probably a lot of people do that now, where they live in a society where you're supposed to fit in, right? But if you're like way ahead of everybody else, but look like you're just doing the same thing they are, then you have more effective privacy, even though people can easily watch and listen to what you're doing.
Okay. So this concept actually is the basis of my favorite book. It's a fictional book. It's called The Circle by Dave Eggers. And it's about how if kind of Google or Google like company took over the world and you didn't have any privacy left. So everything about you had to be shared to the rest of the world. And it comes with like a lot of backlash because people don't want to share their whole stuff, the whole life. And it is technically a dystopian movie book. But the one positive aspect that they kind of add to that puts together if we don't have privacy and stuff falls into the wrong hands, nobody is private about it. So in that case, if it gets to the wrong hands, everyone can see that and everyone already knows that ahead of time. So you can do something about it. So it kind of puts those two ideas together, that no privacy, but people don't really do bad things because everyone's watching them do the bad things.
Yeah.
Wow.
So there was a time, most of you will not believe that this could have existed, but where the stealing of laptops on airplanes was a big deal and you could make a lot of money by stealing laptops. Imagine that now. For one thing, the price of the average laptop is going way down. So, I mean, why would you put yourself at risk to steal something that costs $200 or something? But the other thing, so much has changed about flying that we are so heavily watched and surveilled, right? So there's many other kinds of crime like that that's just not worth it anymore. Hasn't been worth it for some time. So I'm sure there are new kinds of crime, developing all the time. But chances of you're getting your laptop stolen on a plane today is like zero, if assuming you want to actually get on a plane and go somewhere today.
That's a great point, Ashley. I had not thought about that, because you're right. If everyone is watching, then you are more careful and probably, ashamed if they, oh my God, they saw that I stole a reagent from my lab, or, something like that, right? But then at the same time, I think that the more data that these quantum computers get, the better they get at predicting things, and probably at predicting the human condition overall, right? So in a way, I think that in the end, these quantum computers will need more input from humans. And to do that, they need to get into our privacy. And are we prepared as human beings to give that, or are we not? I don't know if I am prepared. I don't think I am at the time. But who knows if in the future I will evolve mentally and I'll be like, yeah, sure, take it.
Resistance is futile, yes. Right.
I think that's an interesting point, though, Eduardo, that you just brought up in terms of whether or not we'd be prepared to give over our data. Because I think even when, I don't know about you guys, like when I got my phone, or like when I started with an iPod. Like that wasn't the first thing in my mind was, what are they going to do with my data? Is my data being collected? I was not aware of that at all. I think maybe now that people are more aware of it, especially given like recent developments in the news about data privacy and all of that, maybe it will change. But I feel like as a general consumer, a lot of the times we're just more concerned with like getting the newest technology and having the fastest phone or the fastest computer or whatever it is than we are about how much of our privacy is given up. Maybe some people are more conscious of it, and I think some might disagree with me, but I think just from general observation, it sometimes feels that way, where people are either number one, not aware of the amount of information they're giving over, or number two, they don't really mind because it just means more targeted information their way or other benefits in other forms.
It can also bring inequality, I feel. For instance, if we think of someone who is part of a family that has several health conditions, probably that person would be charged a higher insurance cost than a person that is healthier, right? And both persons, the healthy and the one that has underlying conditions, they agreed, ideally, to give their information. And because they agreed, there's inequality. The one that has the greater chances of getting sick has greater costs. So that's also, I think, a factor that we need to take into account. How do we use this information that we're giving to bring equal conditions to all humans? I don't know if that is something, it's part of this topic or not at all.
Yeah, well, that becomes easier when you think that the translate-a-thon exists. So, this is a thing that was postulated that would like automatically translate between all languages. People always thought that there would be a text step, right? So you say something, the machine figures out what it is in text and then translates it. But this thing actually converts just from the sound of one language to another. So it means that we're really in a world now where we can talk to everybody else, which already makes the world more equitable. Because when you say, well, make it available to everyone, you're sort of probably thinking in the English-speaking world, but we can really make things available to everyone, period, assuming that the language is a language that is known,
Yeah, what was interesting in that social dilemma video on Netflix, it's actually a documentary about an hour and a half. But anyways, what was interesting in that one, which kind of bounces off what you were saying, Dr. Soles, is that the algorithm in things like Facebook and Instagram doesn't necessarily let you see everything that's online. So if your friends post something about, some of the recent movements that have been going on, you're also posting things like that, you're more likely to see those and not necessarily things that are counter to your beliefs. So it creates, in the video, they highlighted that it creates this really interesting and kind of scary cloud of information that you're surrounded with. So you are driven to believe that everyone else around you thinks like you, but in reality, there's a lot of other information out there. So it is interesting that all this information is free for everyone, but because of the algorithms and the way that Facebook and Instagram cater information towards you, you don't necessarily see it.
I think that's a great point. Like, the less privacy we have, the more effort we need to put in to keep things equal, right? Because the less privacy we have, the more personalized everything will be. So that's a great point right there.
I think that's really cool, Kaylin. Like that's like one of the huge reasons why, our current, even just our political climate is so polarized, and you sort of in your own echo chamber, and it raises the question about, again, back to, not to go back to the ethics part, but I think that's really fascinating. How can these algorithms, how can, machines, like the algorithms that are being chosen, how can they actually have such direct impact on our socio-political, the state of affairs in our world and the state of being? And I think that's such a good example of how it can actually really greatly impact, tangible world.
There's a
phenomena.
side of this that you guys may not have thought about. So as you may know, I have close to 5,000 Facebook friends. A lot of people there are not real friends of mine. I don't really know them, but so a lot of new friends of mine get the idea it'd be really cool to call me up and talk to me. And so these are people from very different cultures, and it can be all times of the day and night, making Facebook calls to me, which I never accept, because I figure, I'm busy, and whatever they want to talk about is unlikely to be of interest to me. But suppose that I accepted all of those calls. It really would put me more in touch with kind of the common person, or the regular person in many different cultures. So maybe there are people out there who accept every Facebook phone call that they get, and have thousands of friends and are becoming very multicultural as a consequence of that.
I think Kaylin and Joel brought up a good point. Like, the motives are different, right? For those tech companies, their motives are profits, right? So they need to show the content that you're most likely to click on, and so you're most likely to see the ads. But that's not the same motive as a single individual trying to get the most accurate and truthful information, right? And so that's where, like, the effort, we need to put conscious effort to ensure we have those barriers versus just profit alone, right? And the human brain is just so imperfect, right? The dopamine or rewards pathway was supposed to be a really productive way for humans to get things done, right? You get something done, you get to survive, it's happy. Whereas a phone can, access that dopamine rewards pathway way easier, right? Our phones are so colorful, and there's so many like cool animations on the phone, and that's why some phones have like grayscale mode, which helps like reduce your phone usage and stuff like that.
Yeah.
So in my witchcraft class, we also learned.
What a transition!
I have a weird.
That's an impressive beginning.
So in my witchcraft class, they talked about how when they learned in universities about alchemy and astrology, because those used to be taught at universities and they used to be studied, their main kind of focus was people thought they were really secretive because they didn't want the knowledge, when they thought that magic was real, to be put into the hands of people who didn't understand it. So I think research has gone a really long way, and science and all this kind of stuff, in letting everyone be able to access things. But when it comes to something like a quantum computer, it might just have to be that we go back to the ways of people who understand it and who have the knowledge to understand the implications of what they are doing, have access to it.
That's a great point. Just really quick, I recently finished listening to an audiobook on Steve Jobs, and his whole life mission was basically computers were just so intimidating to the average user. It was like those alchemy people. Like, it was just segregated to those geeks and like researchers that are using computers. But his goal was to make the computer more approachable, right? More human. And you can see that in all his Apple design language, right? And perhaps one day someone's going to do that to quantum computers. Or maybe alchemy was just like that. If alchemy and like magic was truly like a real thing, then eventually some person would try to make it more approachable, more accessible to the average person, right? Like dumb it down, or just make the features more good for like the average person, right? So that might be like the future of every very specific product, because eventually someone's going to want to make it for the masses.
So Leslie Cormack, the former Dean of Arts, her presentation in this course is really interesting from that point of view. She points out that medicine in the Middle Ages was every bit as complete as medicine is today. They had answers to everything. They had names to put on any problem you might have and ways to explain everything. We might consider them all to be of zero value now and completely fallacious, but it does give you pause to realize that this idea of black magic, white magic, humors, and all those sorts of things were as much of a reality to people living in the Middle Ages as our science is today. There could be parts of our science today that are wrong or woefully incomplete and so on. So we're kind of in a transition toward a period of much greater understanding, right? Just like people in the Middle Ages certainly were. And that continues to go on. So it isn't like when you got sick in the Middle Ages, you go to a doctor and he'd say, well, medicine hasn't evolved to a point where I understand this yet. There's no way he would say that. He said, well, what you have obviously is this and that, and take a few leeches and this kind of spider and so on, and yeah, you'll be well in the morning.
I liked something that Ashley mentioned, and it was that the people that were handling these things needed to understand the importance and the relevance of what they were doing and the responsibility. So I think that's something that we are missing today. We are given these gadgets and it's like, oh, do whatever you want, but we do not take responsibility for the words that we post online, because there is a lot of hate and because they are behind the screen, it's so easy to do it, right? So how do we bring back this sense of this is a powerful thing that we are giving you. Now you need to understand before you use it the relevance that it has to be responsible for your actions or the actions that you do with it. How do you propose, Simon, that we can do this?
Yeah, that's a massive question. This is if you go back to like the past when everyone lived in villages, everyone had to have chickens in their farmlands and stuff like that and do everything. You know what I'm saying? Everyone had to be a generalist. No one was an expert. But as we get more advanced, everyone becomes specialists, right? Like, I have no idea how you make a phone. I have no idea the best arrangement of crops to get the best yield, right? And I have no idea how the egg farmers get their eggs, but we just rely on specialists, that level of trust, right? That those specialists will deliver. And as you're a researcher right now, I have no idea what your research is. I'm sure 99% of people don't know what your research is, but we have that trust in you that as a specialist, you're going to provide the best product or the best information or the best service, right? I think that's the inevitability as we become more advanced. I guess we're limited by our human brain, that we can't be generalists about everything. So we have to just specialize. If we had a powerful brain, I'm sure we could still be generalists and everyone would know everything. But I think that's where the AI comes in, right? And AI could possibly be a generalist of everything, whereas our brain can only be specialists at a very specific topic, and we just gotta trust that everyone plays a role in bolstering humanity as a whole.
So I think that we should realize that there, you know, you might think every term of this course is sort of just a reiteration of the same kind of thing, and just, but there was a student in the winter 2020 rendition of this course, where her final presentation about genetic engineering, the last 6 minutes of it is, I think, the best video that we've ever had, because of this whole counterintuitive thing of, as humanity advances, what are they not looking out for? And so in her story, first of all, as humanity advances, there are certain refuseniks who either can't afford or don't want to, you know, keep up with people getting smarter and more capable and all that kind of thing. And it turns out that the reproductive potential of these increasingly smarter humans ends up to be approximately zero unless you unless you mate with the people who haven't done these advances. And without them, humanity becomes stuck and cannot reproduce at all. And so Salani Agarwal describes that in the last 6 minutes of her presentation, which you can watch. She's assuming that it's the year 2220, and this is the point that humans have reached, where they've sort of optimized everything, and everybody it is, you know, they have perfected themselves to an amazing degree. They're stuck in not being able to make more of themselves without the use of these people who have opted out of doing all this stuff. So it's a really cool story. Just 6 minutes of your life listening to her, and the topic is how many times can you roll nature's dice? How many times can you roll nature's dice?
I just want to add in on that. That's a great point about evolution, and another reason why like AI is probably inevitable. I still remember this definition, I think from Bio 30. It was like, what is evolution, right? I think it was change in allele frequency over time, which is like caused by natural selection. I don't think we're really doing any particularly strong natural selection in this day and age, right? So, and you know, like biological evolution takes millions of years, whereas AI, they don't really have that limit, right? They don't have a reproductive timeline. They just change, right? And so compared to the timeline of AI, like our lifetimes are really stagnant, right? We don't really change. So that's another reason why AI might definitely transcend our consciousness.
So let me just describe the plan for the next 2 teaching sessions. So we'd only have a half hour of like discussion like this, whereas you guys are on your own finding the version of Jack Tazinski's presentation on quantum biology that you like the best. I think what we want you to learn has probably been in his presentations from 2013 on. So it's not like there's a great advantage necessarily of focusing on the more recent presentations. It's also another example of kind of evolution that we got external peer review of the videos, and they said that his video was much too dense, that it's unfair to the students, that it had like 4 times the amount of information you should try to be conveying in an 80-minute class period. We obviously need more lectures. So that's what we did. But on the other hand, your time's limited. So it might be interesting for you to see what it's like trying to take the whole thing in a single lecture. And I would point out, you definitely don't need to learn everything. Like, there are a lot of slides with formulas and details that are just kind of there, not because we want you to learn it, but that's the way that part of the story is, you know? So it's a good kind of example of how to take away the high points, the points of quantum biology that is useful to you. So what I'd like to do for Thursday is have you start watching whichever video you choose to watch, and then come back with questions for Simon and me, and then we'll do the same thing on a week from today, next Tuesday. Yeah, and then the time after that, yes. Ishita is giving a lecture, and then we've got 2 lectures on ethics by Michael Van Manen, and mixed in there somewhere is reading week, which gives you a week off, and then anthrax, which is like a really scary example of the promise and perils of biotech. And yeah, and then we go into your final presentations at the end. So many other things to think about here. One is whether you want to spread out the student presentations at the end. I do not advise doing all 8 on the same day, because I get very fatigued watching 8 student presentations in a row. So I think they would need to be on at least 2 different days, but you can think about how that works into your overall exam schedule and what you would like. So the 4-car garage videography space, we used that for Thanksgiving. We've used it for the Future and all that jazz performance and so on. So it's getting quite organized, and you could use that same space to take pictures of you guys for the cardboard cutouts. That is not a requirement, but Ching Yin Wong, who has already done cardboard cutouts herself and is very happy with them, she's willing to organize this with you, come up with a schedule of getting it done and so on. And it's her idea that we would do this. So anyway, any questions about this current part of the course, quantum?
I have a question about the final presentation and the final essay.
Yes.
Are they on the same topic?
Yes, they are on the same topic. They've always been on the same topic. I'm sure eventually somebody will come up with a cogent reason why we should allow them to do it on two different topics. But so far, the past 9 years, every single student had the same subject for the oral presentation and for the paper. Right.
Okay.
And my concept, you can call it a fantasy, of the first ever weekend that people have spent doing the midterm is that you would realize that this is basically an exam meant to be done in about an hour and a half. It was a little bit tight for time in an 80-minute period, but so it's about an hour and a half of work that you have 4 days to do. So you obviously wouldn't spend the entire 4 days just working on the midterm. But also, if you think, what is the purpose of having an exam? Is it like to frighten the students and stress them out? No, it's supposed to be to solidify knowledge, right? So if we actually do this exam in a way that you enjoy it, you don't do other fun things the same weekend and so on, I think that's an ideal circumstance. And so that's what I'm hoping, that this is actually fun for you. And the other thing is that it's not just me. Like, I'm assuming probably now, like Michael Van Manen will grade the ethics part, and Jack will grade the quantum biology part. Shauna will grade the space part, and so on. So you can think about, who am I writing this stupid exam for, And if it was just me, say, oh boy, Dr. Sola has ruined my whole weekend. But yeah, first of all, there's no way you would want to spend most of your time in that 4-day period doing the midterm. And you shouldn't do all 7 questions on the quantum biology. So pick 4 of them, as the instructions say. And yeah, so you realize, therefore, that you can kind of be on top of like 4 subjects within the kind of broad brush, big picture of quantum biology, particularly if you have sort of unlimited time to write this stuff. So that's my intent. And I hope that we can succeed to create a model for the midterm done over a weekend where you can have fun and it solidifies the knowledge and your own confidence about what you're learning in the course and so on. That's my intent. So any questions about that? Any feeling that I'm heading in the wrong direction? I think this is kind of the right direction. We probably should have always been doing this. So COVID has kind of pushed us into something that is the way the midterm always should have been. Originally we didn't have a midterm because I got the impression from the undergraduate focus group that the easier the course was, the better the students would like it. And you all know that that's not correct, because if your advisor doesn't think highly of the course, then it's not going to be of much value for you to take a course which is just terribly easy and fluffy and so on. So the students actually suggested that we needed the midterm because it was just not rigorous enough without it. Yeah, but anyway, so and the course will continue to, evolve further through wise student input from people just like you, who can say, wouldn't it be much better if you did this or that, And so we would be happy to have other suggestions. we reached a point, you know, we used to have feedback forms and the responses were so telegraphic, just a few words. And one term, the students began writing just reams of information and another thing and another thing. And, you know, been thinking about this a lot, Dr. Solis, and I think you should do this and that. And suddenly the amount of information coming back to me as feedback was really fantastic. And that was a very positive moment in the course. So you can continue that tradition, eh? Like giving good feedback, making the course even better in the future. Yeah. Okay, so we're 9 minutes over. Any other things you want to talk about or interrogate me or Simon about? No? Okay, wow, look at those smiles and stuff. That's okay, well, that's our intent, to keep you smiling, eh? So, yeah. Okay, we'll have a good 2 days then. And so we'll see you at 3 o'clock for a half-hour session with me and Simon and you guys. But we anticipate that your knowledge in quantum biology will be much greater than it is right now because you've watched these very exciting Jack Tazinski videos between now and then. Okay, great. Have a good 2 days, guys. Okay, bye-bye.